Now let's go to a particular use case where we see in detailed manner how the attention scores or at the word level and the sentence level is used to come up with insights which are super helpful in finding out whether model how model is deciding whether something is in this particular case is a misinformation use case, so whether something is true or false, right? So let's go through in detail this approach. So first of all, let's define the problem. What is the problem? So high level detail, if I tell you, there is a claim, right? Let's say Donald Trump, he says that the Obama administration was begging for a meeting with Kim Jong-un. So it's, let's say he said that, right? Whether, and let's say he said it in some rally or something like that, and it published in some news portal or something like that. What you need to find out, the objective is, given this claim, we need to find out whether this is fake or real, whether what he's saying is correct or not, right? So what we need to do, or what we are doing here, we use this claim as a query. We search on the web, let's say using Google API, Bing API, and whatnot, and we get bunch of results. Let's say top K results. K could be 20, 30, 40, so on, right? So top K results. And with this claim and these results, the articles what we get from web, we feed them into the deep neural net, and we do some processing which we don't have to worry about, and then it says that it is fake or real, right? So your model predicts the label that it is fake or real, right? So this is the task. So what is happening is like this, right? So claim is there. You, let's say, use the Google search API, and in a particular top 20, let's say you are taking top 10 to 20 results. In one of the results, if you open it, if, let's say it's from Washington Post, it says that no public records or news articles show that Obama tried to meet with Kim, right? So it kind of refutes to what the claim was, right? So claim was the Obama administration was begging for a meeting with Kim Jong-un, right? And you feed all this to the model. Model says whether it's false or not. On top of that, it also generates a kind of a explanation, right? So this is what the objective is. Other objective. So one of the objective is to predict the label, but other objective is to have some explanation also, and then we'll see how it is done in this model. So a bit detail of the model also let's see, and which will give you some idea that how these attention scores are working and how we compute the attention scores, right? So given this model is not super difficult. So what we do here at the input side, input layer, or at input stage, we have these red blocks. What you are seeing, these are, let's say, claim, and each word is represented in some sort of embedding. It could be word-to-vec embedding, could be glove embedding, and so on. So in this particular paper, it is glove embedding. So for each word you have glove embedding, you represent in using glove vectors, glove embedding vectors, and then you concatenate the documents received from the web when you use the claim as a query, right? So you document embedding. So document words are also embedded using glove embedding, and you concatenate them, you feed them in sequence to the bidirectional LSTM, right? So at each time step, one word goes in, and so on. You know the working of the bidirectional LSTM, and you get these hidden representations, H1 1, H1 2L. So for this, let's say L is the length of the claim, and from HN1 to HNL, let's say this is the length of the document, and so on. And on top of that, you have another thing. This is called aspect vector, and you can, as of now, you can treat it as a vector or representing something, right? And I will tell you later what this aspect vector is, but treat it as a randomly initialized vector A, right? Then what you need to do, given these hidden states, and we have recently, we had covered in RNN also, but in today's lecture also we had covered it, how you can compute a vanilla attention with given hidden states of LSTM. So each of these hidden states go into this tiny neural net having a, let's say, ReLU activation, and this aspect vector also goes in. So this is additional thing. So we had discussed there was no aspect vector, but there is a aspect vector, and I'll tell you the intuition or logic behind aspect vector, why do we need it. And you compute these alphas, alpha 1 1, alpha 2, alpha 1 L, and whatnot, right? So all these alphas are calculated. You multiply back to these hidden states with these alphas, and you kind of sum them up. So when you sum them up for this sequence from 1 1 to 1 L for claim, so you will get a one sentence. And similarly, you might have multiple sentence, right? So you get the sentence representation, which is kind of attended representation of the sentence, because you are multiplying, weighting them using these attention scores alpha, right? And then what you need to do, when you get these sentence representations, you again have another bidirectional LSTM. So it's a kind of a hierarchical encoding. So you have in higher hierarchy, you have the sentence level bidirectional LSTM, which encodes the sentences. It produces also the hidden states at the sentence level for each of the sentences, and these again go to a tiny neural net, similar kind of tiny neural net, and this aspect vector is again copied here. You get the aspect vector also. It computes the betas, so these attention scores at the sentence level. Then what you need to do, you multiply these hidden states with betas, and now you need to sum them up. This should be summation here. Yeah, you need to sum them up, and you get the document representation at the end, right? So up till now, what you did from the claim and the document received from the web, you encoded in hierarchical fashion. You encoded at the word level bidirectional LSTM with the word level bidirectional LSTM, and then you attended it using attention scores, and then you get the sentence representation. You feeded the sentence representation to the bidirectional LSTM at the sentence level, and you get a document representation, which is overall representation of this whole document, right? You can treat this claim plus document as a document here, right? So in terms of equation also, you can see that we computed using a softmax, and we applied 10H rather than ReLU. Yeah, it should have been 10H. So we use 10H to compute the attention scores, and then we multiply the respective corresponding alphas with word level hidden states, and respective corresponding betas with the sentence level hidden states, and we kind of get the sentence representation at the word level and document representation at the sentence level, right? So moving forward, this is how the overall model looks like. So this was the previous one was one of the branch of this model, and we have three of similar branches, and the branches are very same. The legs, these three legs are very similar. You can see that these things are copied here. So claim embedding plus the document embedding, and this thing is same, right? So which we have seen underneath each of these submodule, we have similar thing repeated. Only change is this aspect vector. So in case of subject model, the aspect vector is a subject, is a topic of the document, and or the claim, right? So a topic of the claim. And in the author model, this aspect vector is the who is the speaker of that claim. So in our example, it was Donald Trump. It could be Barack Obama and whatnot. In domain model, the aspect vector is the domain of the article which we have retrieved from the web, right? So let's say it could be NY Times, it could be Washington Post and whatnot, right? So those are the domains. So only these things are changed, and then we get document representation from each of these, right? So you get document representation of each of these. We concatenate these document representation coming from different models, and then we apply the classifier on top of it. So softmax, and we get the classification done, right? So this is the overall model. Now we'll see, and there are some other details which we can also omit, but quickly we can cover. So you might be wondering what this aspect vector is. So what this aspect vector is, we haven't discussed this much. So as you have seen for word representation, we are using glove embeddings to represent the words. But what about the aspects? So domain, subject, and author. So what did we do? We, for each of, let's say for case of speaker, so we started with number of people which were there in the corpus, and each of them were represented using n-dimensional vector, and these are randomly initialized, right? So tending to 0, very close, smaller values, and we initialize this. We use these values with the corresponding sample. Let's say sample is coming, speaker is Donald Trump, so we'll be using Donald Trump embedding now as a aspect vector. And from the rest of the model, you will get the backprop or the loss. You will get the backpropagation of the loss. It will go to this tiny neural net what we have seen here, right? So it will, this backpropagation coming from the softmax, which is somewhere here, it will go till here, and it will also go to these tiny neural nets, right? So with the backprop, these weights, and these are trainable embeddings, so these weights will also change. So in each iteration, in each epoch, there might be different set of speakers might be there, so their weights might change. And at the end of the training, you will get all the weights or the vectors for all the embeddings for all the speakers will be learned, right? So it will be learned. And what you need to do at the test time, you need to freeze them, and at the inference time, and you need to utilize them, right, in the model, right? So you don't have to, you need to freeze them at the test time, right? So that's what you need to do. Okay, so now we get to the part where we explain some of the internals of this model, whether this model learned something or not. So one of the things what we tried is visualizing the embeddings learned through this, right? So we learned the embeddings for speakers, let's say Donald Trump, Barack Obama, and so on. We learned the embeddings for domains, NY Times, Washington Post, and whatnot. And we learned the embeddings for topics, like say nuclear, or it could be politics, it could be environmental, climate change, and whatnot, right? So we learned those embeddings. So in this case, we plotted the speaker embedding or author embedding, you can call it, with the 2 dimension of TSNE. So, and it turns out that model is not just able to cluster the people involved in more true news versus fake news. So let's say Donald Trump here, George W. Bush here, right? So they are maybe involved with more fake news or misinformation, whether on the other hand, Bernie Sanders and clearly like a crookie Bobby Jindal, and those people are not kind of involved much in misinformation. But on the other hand, you can also see in the embedding space, these embeddings like Donald Trump and Ted Cruz, they are closer to each other, and Bernie Sanders and Barack Obama, Hillary Clinton are closer to each other. So model also able to capture the ideology. They belong to same party, they have the same vision, and so on, right? So model is able to capture that also. In case of topic embedding, it turns out that federal law and healthcare and climate change, these are having very different kind of pattern here. So you can see federal law, when it comes to civil right, federal law, they are not much involved in the misinformation. But climate change and healthcare, and they are closer in the embedding space, they are involved much in the more in misinformation and disinformation kind of posts. Interestingly, when we visualize the domain embedding, we saw that some of the domains or the portals having reputable a kind of a reputation on the web and in the society are clustered together, and some of the some of the portals which were not so much trustworthy, and they are kind of clubbed together. So more shady ones are kind of clubbed together, and there were some portals which are in between, so they might get involved. They have sometimes true news and they might also get some fake news or disinformation, misinformation also posted on their portal. And so the other important thing what we did here, that given the claim there is a substantial evidence of voter fraud, let's say said by Donald Trump, so author is Donald Trump, and the domain this particular article retrieved from is guardian.com, and the subject is election. So what we did for each of the legs of the model, which we have seen 3 branches of the model, we kind of extracted the word level attention. So you can see these highlights, right? So the depth of the color shows that how important that word is. So let's say claims, it's not having much depth, so it's not much given much attention score. But in case of documents, White House, it's getting more attention score, right? Specifically in Guardian.com, we can see words which are rare, glaringly empty and voter fraud and so on. So they are getting selected. And in case of subject, based on the topical attention, topic driven attention, we can see that the things related to elections are getting election integrity and evidence, voter fraud, and those are getting selected, right? And what we did using the and on top of that, we get a attention score at the sentence level also, because it's a hierarchical encoder which having hierarchical attention. So for each sentence also, how important this sentence was for this particular claim to debunk or maybe to support or refute, and less importance, more importance, less importance and more importance, you get a score for there. And they proposed an algorithm which combines the word level attention and the sentence level attention to extract sentences as an evidence. So it's kind of giving evidential summary. So it says that documents disapprove White House vote for fraud claims, says ex-member of Trump Commission, most voting rights expert view in-person voter fraud as passingly rare, right? So it kind of refutes to this claim, right? So now you can see, given this model correctly predicts what would be the label. Let's say it says false, right? So not only just predicts the label as false, but also it gives you evidence that this is why model thinks that this should be false, right? And at the word level also, it kind of gives you keywords that because of these keywords, model thinks that this should be false, not true, right? So the last example of the same I've taken, which is a recent paper submitted to NACL, and where we have multimodal scenario. So we have image and text both, and again the use case is misinformation detection. But we not only just have, let's say, claims or the tweets, posts, we also have corresponding images which are posted side by side with that post, right? So just to quickly go through the model itself. So what we did here, this is the text. We applied the bird to get the representation of each of the words here which are there. And what we did from these images with a with one model which you can see in the paper, that we get the patch embedding. So for each of the patches, it broken down into the patches, and we get the patch embeddings, and there's a sequence of patches, right, for the images. So whole images is divided into patches, and for each patch we have an embedding. So this is the sequence of patches, this is sequence of tokens, and tokens, the embeddings are coming from BERT, right? What we did is we concatenated these two sequence of tokens and sequence of patches, and then after concatenation we apply a transformer encoder. So we'll full-fledged self-attention and all the blocks of the transformer are there. So we apply a transformer encoder and we get a one representation of it. On top of that, what we did is we converted the text to a graph and the image also to a graph, and we call it text scene graph and visual scene graph, right? And with the help of a pre-trained model. So both of these are pre-trained model which is like publicly available, open access, so you can go through them. And we generated the graph out of it. We generated the images of the graph out of images, and applied the graph neural net, which we haven't covered in this course, which is beyond the syllabus of this course. And we get the representation using mean pool. You get a one representation from this GNN and another representation from this visual scene graph, and you concatenate at the end, right? Finally, this encoded representation from the text and patch sequence, and from TSG and VSG, text scene graph and visual scene graph, which is coming from GNN, we concatenate finally and apply a non-linearity, and then let's say we learned a classifier using sigmoid. It's a binary classification task, right? So this was the overall model which we proposed. And then for a cherry-picked example, we can see how model is deciding what words are important, what region of images are important. So we use shapely values and we apply shapely, and we saw that the words are given importance, like Carolina, Ronald Reagan debate, and TPM TV, right? So here also TPM is getting selected, and this face is getting selected. So some sort of region which is important is also you will get from the shapely values. On top of that, in another example, you see that Obama promises abortion in public plan, right? So this was the case, and model focused on promises abortion, and the plan might be in the future. It also says that stand up for the woman. This is also getting selected, so it kind of relates to it that abortion is somehow related to the women and some of the regions which are important for it, right? So it kind of gives you some idea that model is kind of targeting a particular region which is important, right? Which is important for the model to predict something. It is kind of giving emphasis to particular word which is which are important indeed when you see these visualization, these explainability aspects, right? So in the next set of class, we'll be learning about some of the topics which we haven't covered yet, and which is biases and ethics related to NLP and specifically LLMs. So why ethics and the biases are important when it comes to LLMs. Thanks.